Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The formation of crystals is, in many respects, one of the most quietly remarkable phenomena observable in the natural world. And yet it proceeds with such unhurried regularity and such predictable adherence to fundamental physical laws that one might be forgiven for finding the entire subject matter to be among the least dramatic of all geological and chemical processes. A crystal, in the most basic and technically precise definition available to modern science, is a solid material whose constituent atoms, molecules, or ions are arranged in a highly ordered microscopic structure, forming a crystal lattice that extends in all directions with repeating three-dimensional patterns. This definition, while perhaps not immediately stirring to the casual observer, contains within it the essential character of crystalline matter, which is that the arrangement of particles follows strict geometrical rules that have been understood in progressively greater detail since at least the 17th century. The study of crystal formation, or crystallogenesis, as it is sometimes called in more formal academic literature, encompasses a broad range of scientific disciplines, including mineralogy, chemistry, physics, and materials science. The process by which dissolved substances, molten materials, or vapors transform into solid crystalline structures has been the subject of careful investigation for several hundred years, and the accumulated body of knowledge on this topic is both vast and, it must be said, extraordinarily detailed in its specificity. The temperature at which a particular substance begins to crystallize, the rate at which crystal faces develop, the precise angles between adjacent crystal faces, and the manner in which impurities become incorporated into a growing crystal lattice are all matters that have been measured, catalogued, and analyzed with painstaking thoroughness by generations of scientists working in laboratories and field stations around the world. To begin at the most fundamental level, one must consider the nature of the chemical bond and the manner in which atoms and ions interact with one another in solution, in the melt, or in the vapor phase. When a substance is dissolved in a solvent, its constituent particles are dispersed throughout the liquid medium, surrounded by solvent molecules, and maintained in a state of relatively free movement by thermal energy. The concentration of dissolved substance relative to the maximum amount that the solvent can accommodate at a given temperature is described by the concept of saturation. A solution is said to be saturated when it contains the maximum amount of dissolved solute that can be maintained in equilibrium with undissolved solid at a particular temperature and pressure. When the concentration of dissolved material exceeds this saturation point, the solution becomes supersaturated, and it is in this condition of supersaturation that the initial stages of crystal formation become thermodynamically favorable. The degree of supersaturation required to initiate crystallization varies considerably from one substance to another and depends upon a number of factors, including the nature of the solute, the identity of the solvent, the temperature, the presence or absence of seed crystals or other nucleation sites, and the rate at which supersaturation is achieved. For common table salt, sodium chloride, dissolved in water at a temperature of approximately 20 degrees Celsius. The saturation concentration is roughly 36 grams per 100 milliliters of water. To achieve supersaturation, one might slowly evaporate some of the water, thereby increasing the concentration of dissolved sodium chloride beyond the 36-gram threshold, or one might cool a warm, saturated solution. Since the solubility of sodium chloride decreases, albeit only very slightly, with decreasing temperature. The difference in solubility between 20 degrees and 0 degrees Celsius for sodium chloride is, in fact, remarkably small, amounting to a decrease of only about 1 gram per 100 milliliters, which is one of the reasons why sodium chloride is not typically the first substance that crystallography students encounter in their practical exercises. The initial event in crystal formation is nucleation, which refers to the spontaneous assembly of a small cluster of solute particles into an ordered arrangement that can serve as the foundation for further crystal growth. Nucleation is conventionally divided into two categories: primary nucleation, which occurs in the absence of any pre-existing crystalline material, and secondary nucleation, which is induced by the presence of existing crystals or crystal fragments. Primary nucleation is further subdivided into homogeneous nucleation, which takes place entirely within the bulk of the supersaturated solution without the influence of any foreign surfaces, and heterogeneous nucleation, which is facilitated by the presence of foreign particles, container walls, dust, or other surfaces that can lower the energy barrier to nucleus formation. Homogeneous nucleation is, from a purely thermodynamic perspective, the most straightforward to analyze, but also the most difficult to observe in practice, since it requires the spontaneous formation of a stable nucleus from the random thermal motion of dissolved particles. The classical nucleation theory, which was developed in its modern form during the early to middle decades of the 20th century, describes the free energy change associated with the formation of a spherical nucleus of radius R as the sum of two competing terms. The first term is a volume term, which is negative and proportional to the cube of the radius, reflecting the thermodynamic driving force for crystallization that arises from the difference in chemical potential between the supersaturated solution and the crystalline solid. The second term is a surface term, which is positive and proportional to the square of the radius, reflecting the energy cost of creating a new solid-liquid interface. The competition between these two terms gives rise to a critical nucleus size, below which the cluster is thermodynamically unstable and tends to dissolve back into solution, and above which the cluster is stable and tends to grow spontaneously. The critical radius for nucleation can be calculated from the expression R * equals 2 gamma Vm / RTLNS, where gamma represents the interfacial tension between the crystal surface and the solution. Vm is the molar volume of the crystalline solid. R is the universal gas constant with a value of approximately 8.314 joules per mole per Kelvin. T is the absolute temperature in kelvins. And S is the supersaturation ratio, defined as the actual concentration divided by the equilibrium saturation concentration. For many common inorganic salts crystallizing from aqueous solution at room temperature, the critical nucleus size is on the order of 1 to 10 nanometers, corresponding to clusters containing anywhere from a few dozen to several thousand atoms or ions. The rate of homogeneous nucleation, which describes the number of stable nuclei formed per unit volume per unit time, is an exponentially sensitive function of the supersaturation ratio. At low levels of supersaturation, the nucleation rate is effectively zero, since the energy barrier to forming a critical nucleus is too high to be overcome by thermal fluctuations within any reasonable experimental time frame. As the supersaturation increases, the energy barrier decreases and the nucleation rate increases dramatically, often by many orders of magnitude over a relatively narrow range of supersaturation values. This extreme sensitivity of nucleation rate to supersaturation is one of the defining characteristics of the crystallization process and has important practical consequences for the control of crystal size distribution in industrial crystallization operations. Heterogeneous nucleation, by contrast, occurs at significantly lower levels of supersaturation than homogeneous nucleation because the foreign surface provides a template or scaffolding that reduces the effective surface energy cost of forming a nucleus. The reduction in the energy barrier depends upon the contact angle between the crystalline nucleus and the foreign surface, with smaller contact angles corresponding to greater reductions in the barrier height. In practical crystallization systems, heterogeneous nucleation is almost always the dominant mechanism for primary nucleation, since it is virtually impossible to prepare a solution that is entirely free of foreign particles, dust, and surface irregularities. Even in carefully filtered and purified solutions, the walls of the crystallization vessel itself serve as heterogeneous nucleation sites, and the degree of supersaturation required to initiate crystallization in a glass beaker is typically much lower than would be predicted by the theory of homogeneous nucleation alone. Once a stable nucleus is formed, whether by homogeneous or heterogeneous means, the crystal enters the growth phase, during which additional solute particles are incorporated into the crystal lattice at the crystal solution interface. Crystal growth is a complex process that involves several sequential steps: the transport of solute from the bulk solution to the vicinity of the crystal surface by diffusion and convection, the adsorption of solute particles onto the crystal surface, the migration of adsorbed particles across the surface to energetically favorable incorporation sites, and the actual integration of the particle into the crystal lattice at a kink site, step edge, or other defect. Each of these steps has its own characteristic rate, and the overall rate of crystal growth is determined by whichever step is the slowest under the prevailing conditions. In many crystallization systems, particularly those involving the growth of large, well-formed crystals from solutions with moderate to high levels of supersaturation, the rate-limiting step is the diffusion of solute through the boundary layer of depleted solution that surrounds the growing crystal. This boundary layer, sometimes called the Nernst diffusion layer, has a thickness that depends upon the hydrodynamic conditions in the crystallizer, with typical values ranging from approximately 10 to 100 micrometers in unstirred solutions and from 1 to 10 micrometers in well-stirred systems. The concentration of dissolved solute decreases from its bulk value at the outer edge of the boundary layer to a value close to the saturation concentration at the crystal surface, and this concentration gradient provides the driving force for the diffusive transport of solute toward the growing crystal. The morphology of a growing crystal, meaning the relative sizes and shapes of its various faces, is determined by the relative growth rates of different crystallographic directions. Crystal faces that grow slowly tend to become large and prominent in the final crystal habit, while faces that grow rapidly tend to shrink and may eventually disappear entirely as they are overtaken by slower-growing adjacent faces. This relationship between growth rate and face prominence was recognized as early as 1669 by the Danish naturalist Nicholas Steno, who observed that the angles between corresponding faces of quartz crystals are always the same, regardless of the overall size or shape of the crystal specimen. This observation, known as Steno's law of constancy of interfacial angles, was one of the earliest quantitative discoveries in the field of crystallography and remains a fundamental principle of the discipline to this day. The external shape or habit of a crystal is influenced by a number of factors beyond the inherent growth rates of different crystallographic directions. The presence of impurities in the growth solution can selectively adsorb onto certain crystal faces, inhibiting their growth and thereby altering the crystal habit. The supersaturation level affects the relative growth rates of different faces, with higher supersaturation tending to favor more isotropic growth and lower supersaturation tending to produce more elongated or tabular crystals. The temperature of the growth solution, the pH, the presence of specific additives, and the hydrodynamic conditions in the crystallizer can all influence the final crystal morphology in ways that have been studied extensively, but are not always fully predictable from first principles. The internal structure of a crystal is described by its crystal system, of which there are 7 in classical crystallography: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. These 7 crystal systems are defined by the relationships between the lengths and angles of the unit cell, which is the smallest repeating structural unit that, when translated in 3 dimensions, generates the entire crystal lattice. The cubic system, for example, is characterized by a unit cell in which all 3 edge lengths are equal and all 3 angles between edges are 90 degrees. Sodium chloride, the common table salt mentioned earlier, crystallizes in the cubic system with a face-centered cubic structure in which each sodium ion is surrounded by 6 chloride ions and each chloride ion is surrounded by 6 sodium ions, forming an arrangement that extends uniformly in all directions. The tetragonal system is similar to the cubic system in that 2 of the 3 edge lengths are equal and all 3 angles are 90 degrees, but the 3rd edge length differs from the other 2. Tin dioxide, also known as cassiterite, is an example of a mineral that crystallizes in the tetragonal system with edge lengths A equals B equals 4.738 angstroms and C equals 3.187 angstroms at standard conditions. The orthorhombic system has three mutually perpendicular axes of unequal length, as seen in the mineral olivine, which has unit cell dimensions of approximately equals 4.76 angstroms, B equals 10.20 angstroms, and C equals 5.98 angstroms. The hexagonal system is defined by a unit cell with two equal edge lengths at 120 degrees to each other in a basal plane, with a third axis of different length perpendicular to that plane and beryl. The mineral from which emerald and aquamarine derive their gemological significance is a well-known example of a hexagonal crystal with unit cell parameters at equals 9.21 angstroms and C equals 9.19 angstroms. The trigonal system, which is sometimes treated as a subdivision of the hexagonal system rather than as a separate crystal system in its own right, is characterized by a single axis of threefold rotational symmetry. Quartz, silicon dioxide, is perhaps the most familiar mineral to crystallize in the trigonal system, with unit cell dimensions of equals 4.913 angstroms and C equals 5.405 angstroms at room temperature. The monoclinic system, in which one of the three interaxial angles differs from 90 degrees while the other two are equal to 90 degrees, encompasses a large number of common minerals, including gypsum. With unit cell parameters at equals 5.68 angstroms, B equals 15.18 angstroms, C equals 6.29 angstroms, and the non-right angle beta equals 118.4 degrees. Finally, the triclinic system, the least symmetric of the 7 crystal systems, has 3 unequal edge lengths and 3 unequal interaxial angles, none of which is necessarily 90 degrees, and is represented by minerals such as albite feldspar, with unit cell dimensions equals 8.14 angstroms, B equals 12.79 angstroms, C equals 7.16 angstroms, alpha equals 94.3 degrees, beta equals 116.6 degrees, and gamma equals 87.7 degrees. Within each of the 7 crystal systems, the possible arrangements of lattice points are further classified into 14 Bravais lattices, which describe the different ways in which a unit cell can be constructed by placing lattice points at the corners and, in some cases, at the centers of the faces or the body of the unit cell. The French physicist Auguste Bravais demonstrated in 1850 that there are exactly 14 distinct lattice types that are consistent with the translational symmetry requirements of three-dimensional periodic structures. These 14 Bravais lattices, combined with the various point group symmetries that describe the rotational and reflective symmetry elements present at each lattice point, give rise to a total of 230 distinct space groups, which represent all the possible symmetry arrangements that a three-dimensional crystal can adopt. The enumeration of these 230 space groups was completed independently by the Russian crystallographer Evgraf Fedorov in 1891 and the German mathematician Arthur Schauffele in 1892, and their classification remains the foundation of modern structural crystallography. The process of crystal formation from a melt, as opposed to from a solution, involves somewhat different physical mechanisms, although the fundamental principles of nucleation and growth remain applicable. When a molten substance is cooled below its melting point, the thermal energy of the constituent particles decreases, and at some point the particles begin to adopt the ordered arrangement characteristic of the crystalline state. The temperature at which this transition occurs under equilibrium conditions is the melting point, which for a pure substance is a precisely defined thermodynamic quantity. For silicon dioxide in its most common crystalline form, alpha quartz, the melting point is 1713 degrees Celsius at atmospheric pressure. For aluminum oxide, corundum, the melting point is 2072 degrees Celsius. For iron, the melting point is 1538 degrees Celsius, at which point the body-centered cubic delta iron phase transforms upon cooling first to face-centered cubic gamma iron at 1394 degrees Celsius, and then to body-centered cubic alpha iron at 912 degrees Celsius. The crystallization of minerals from magma, which is the molten or partially molten rock material found beneath the Earth's surface, is one of the most geologically significant examples of crystal formation from a melt. Magma is a complex multi-component silicate liquid containing dissolved gases, and the order in which different minerals crystallize from a cooling magma body is determined by the composition of the melt and the melting points of the various mineral phases present. This crystallization sequence was first systematically described by the Canadian-American petrologist Norman Levi Bowen in the early 20th century, and the resulting Bowen's reaction series has been a cornerstone of igneous petrology for over 100 years. According to Bowen's reaction series, the first minerals to crystallize from a typical basaltic magma are olivine and calcium-rich plagioclase feldspar, which begin to form at temperatures around 1200 degrees Celsius. As the magma continues to cool, pyroxene replaces olivine in the crystallizing assemblage, and the plagioclase composition shifts progressively toward more sodium-rich varieties. Further cooling produces amphibole, then biotite mica, and finally, at temperatures below approximately 700 degrees Celsius, the last minerals to crystallize are potassium feldspar, muscovite mica, and quartz. The rate at which magma cools has a profound influence on the size and quality of the crystals that form. Magma that cools very slowly, as in the interior of a large intrusive igneous body such as a batholith, allows ample time for atoms and ions to diffuse through the melt and attach themselves to growing crystal faces, resulting in the formation of large, well-developed crystals that can be several centimeters or even meters in length in exceptional cases. Granite, which is the most common intrusive igneous rock, typically contains crystals of quartz, feldspar, and mica that range from approximately 2 to 5 millimeters in diameter, giving the rock its characteristic coarse-grained or phaneritic texture. In contrast, magma that cools rapidly, as when lava is erupted onto the Earth's surface, produces much smaller crystals, or, if the cooling is sufficiently rapid, no crystals at all. Basalt, the most common extrusive igneous rock, has a fine-grained or aphanitic texture in which individual crystals are generally too small to be seen with the unaided eye, typically measuring less than 1 millimeter in diameter. When lava cools extremely rapidly, as when it is quenched by contact with water, the result may be volcanic glass or obsidian, in which the atoms are frozen in a disordered, amorphous arrangement that lacks the long-range periodic order of a true crystal. The formation of crystals from the vapor phase, known as vapor deposition or sublimation crystallization, is yet another mechanism by which crystalline materials can be produced. The most familiar natural example of vapor phase crystallization is the formation of snowflakes, in which water vapor in the atmosphere condenses directly into ice crystals without passing through the liquid phase. The conditions under which snow crystals form have been studied with particular thoroughness by the Japanese physicist Yukichiro Nakaya, who in the 1930s and 1940s conducted extensive experiments on the growth of artificial snow crystals in a laboratory setting. Nakaya found that the morphology of snow crystals is primarily determined by the temperature and supersaturation of the water vapor from which they grow. At temperatures near -2 degrees Celsius, thin hexagonal plates tend to form. At around -5 degrees Celsius, columnar or needle-like crystals predominate. Near -15 degrees Celsius, the elaborate branched dendritic crystals that are most commonly associated with the popular image of a snowflake are produced. And at temperatures below -25 degrees, the crystals revert to simpler columnar and plate-like forms. The hexagonal symmetry of snow crystals arises from the hexagonal crystal structure of ice, which is the ordinary form of ice found under terrestrial atmospheric conditions. In the crystal structure of ice, each water molecule is hydrogen bonded to 4 neighboring water molecules in a tetrahedral arrangement, and the overall lattice has hexagonal symmetry with unit cell parameters equals 4.52 angstroms and C equals 7.36 angstroms at a temperature of -10 degrees Celsius. The six-fold symmetry visible in the macroscopic morphology of a snow crystal is a direct expression of this underlying hexagonal lattice symmetry, amplified and made visible by the growth process that selectively extends the crystal in directions determined by the lattice geometry and the growth conditions. The phenomenon of polymorphism, in which a single chemical substance is capable of crystallizing in more than one distinct crystal structure, provides an additional layer of complexity to the study of crystal formation that has occupied the attention of mineralogists and chemists for well over 2 centuries. The term polymorphism itself was coined by the German mineralogist Eilhard Mitscherlich in 1822, following his observations that certain chemical compounds, such as the phosphates and arsenates of various metals, could adopt different crystalline forms depending upon the conditions of their formation. Perhaps the most widely cited example of polymorphism is that of carbon, which can crystallize either as diamond, in the cubic crystal system with each carbon atom tetrahedrally bonded to 4 neighbors in a 3-dimensional network, or as graphite, in the hexagonal crystal system with carbon atoms arranged in planar sheets of hexagonal rings that are held together by relatively weak van der Waals forces. The physical properties of these two polymorphs are, as might be expected from their dramatically different crystal structures, remarkably dissimilar. Diamond is the hardest known naturally occurring material, with a Mohs hardness of 10, while graphite is one of the softest, with a Mohs hardness of 1 to 2. Diamond is transparent and has a refractive index of 2.417, making it one of the most brilliant gemstones, while graphite is opaque and dark gray to black in color. Calcium carbonate presents another instructive example of polymorphism, as it can crystallize in at least 3 distinct crystal structures: calcite, which belongs to the trigonal crystal system; aragonite, which belongs to the orthorhombic crystal system; and vaterite, which belongs to the hexagonal crystal system. Calcite is the thermodynamically stable form of calcium carbonate under ambient conditions at the Earth's surface, with a density of 2.71 grams per cubic centimeter and unit cell parameters at equals 4.989 angstroms and C equals 17.062 angstroms in the hexagonal setting of the trigonal lattice. Aragonite, with a density of 2.93 grams per cubic centimeter and unit cell parameters at equals 4.961 angstroms, B equals 7.967 angstroms, and C equals 5.741 angstroms, is metastable under ambient conditions, but is the stable form at higher pressures, such as those found at depths greater than approximately 350 meters within the Earth's crust. Vaterite, the least stable and most rarely encountered of the 3 polymorphs, has a density of 2.65 grams per cubic centimeter and tends to transform rapidly into calcite or aragonite under most geological conditions. The transformation between polymorphs can occur through reconstructive mechanisms in which the crystal structure is completely dismantled and rebuilt, or through displacive mechanisms, in which the atoms undergo relatively small shifts in position without breaking any bonds. The transformation of alpha quartz to beta quartz at a temperature of 573 degrees Celsius at atmospheric pressure is an example of a displacive transformation, in which the silicon-oxygen tetrahedra that make up the quartz framework rotate slightly relative to one another, changing the symmetry from trigonal to hexagonal without fundamentally altering the connectivity of the structure. This transformation is accompanied by a small but measurable change in the unit cell dimensions, with the parameter increasing from 4.913 angstroms to 5.01 angstroms and the C parameter decreasing from 5.405 angstroms to 5.47 angstroms, and by a correspondingly small change in the density of the material. The role of water in crystal formation processes is a topic of considerable scientific and practical importance that merits detailed examination. Many minerals form in the presence of water, whether as precipitates from aqueous solution, as products of hydrothermal alteration, or as components of evaporite sequences that develop when bodies of water gradually dry up. The evaporation of seawater, for instance, produces a characteristic sequence of crystalline precipitates that has been observed and documented in numerous geological settings around the world. As seawater evaporates, the first mineral to precipitate is typically calcite, calcium carbonate, which begins to crystallize when the volume of the original seawater has been reduced to approximately 50% of its initial value. Continued evaporation leads to the precipitation of gypsum, calcium sulfate dihydrate, at approximately 20% of the original volume. Halite, sodium chloride, begins to crystallize when the volume has been reduced to approximately 10%, and the final stages of evaporation produce a complex assemblage of potassium and magnesium salts, including sylvite, carnallite, and kyanite at volumes below 5% of the original seawater volume. The formation of crystals in hydrothermal systems, where hot aqueous fluids circulate through fractures and pore spaces in rocks at temperatures ranging from approximately 50 degrees Celsius to over 500 degrees Celsius, is responsible for the creation of many economically important mineral deposits. Hydrothermal fluids are typically enriched in dissolved metals and other elements that have been leached from the surrounding rocks, and as these fluids cool, mix with cooler groundwater, or undergo changes in pressure or chemical composition, the dissolved substances may crystallize to form veins, disseminations, or massive ore bodies. The formation of quartz veins, which are among the most common products of hydrothermal activity, occurs when silica-saturated fluids cool below the solubility limit of quartz, causing the dissolved silicon dioxide to precipitate as crystalline quartz. The solubility of quartz in pure water at a pressure of 1 kilobar increases from approximately 0.18% at 200 degrees Celsius to approximately 0.68% at 500 degrees Celsius. And it is this strong temperature dependence of solubility that drives the precipitation of quartz as hydrothermal fluids cool during their ascent toward the Earth's surface. The growth of crystals in caves, known as speleothems, provides some of the most visually striking examples of natural crystal formation. Stalactites, which grow downward from cave ceilings, and stalagmites, which grow upward from cave floors, are both formed by the slow precipitation of calcium carbonate from dripping water that has percolated through limestone above the cave. The rate of stalactite growth depends upon the rate of water flow, the concentration of dissolved calcium carbonate in the dripping water, the rate of carbon dioxide degassing from the water, and the temperature and humidity conditions within the cave. Typical growth rates for stalactites range from approximately 0.01 to 0.3 millimeters per year, meaning that a stalactite 1 meter in length may have taken anywhere from 3,000 to 100,000 years to form. The internal structure of stalactites is typically characterized by a central canal through which water flows, surrounded by concentric layers of calcite that have been deposited over time, creating a cross-sectional pattern that is not entirely dissimilar to the growth rings of a tree. The formation of crystals within living organisms, known as biomineralization, represents a fascinating intersection of biology and crystallography that has been the subject of increasingly intensive research in recent decades. Many organisms produce crystalline materials as structural components, protective coverings, or storage depots for essential elements. The shells of mollusks, for example, are composed of calcium carbonate in the form of either calcite or aragonite, or frequently a combination of both, organized into elaborate multilayered structures that possess mechanical properties far superior to those of the individual mineral components. The nacre, or mother of pearl, that lines the inner surface of many mollusk shells consists of thin tablets of aragonite, each approximately 0.5 micrometers thick and 5 to 10 micrometers in diameter, arranged in a brick-like pattern with thin layers of organic matrix material between them. This hierarchical architecture gives nacre a fracture toughness that is approximately 3,000 times greater than that of pure aragonite, an achievement that has inspired considerable interest in the field of biomimetic materials design. The bones and teeth of vertebrate animals, including humans, are composed of a crystalline calcium phosphate mineral known as hydroxyapatite, with the chemical formula Ca10, PO4, 6, OH, 2, and a hexagonal crystal structure. The crystals of hydroxyapatite in bone are extremely small, typically measuring approximately 50 nanometers in length, 25 nanometers in width, and 2 to 3 nanometers in thickness. And they're intimately associated with collagen fibers and other organic components that together create the composite material that gives bone its remarkable combination of stiffness and toughness. The process by which hydroxyapatite crystals form within the collagen matrix of developing bone is a complex and highly regulated biological process that involves the controlled release of calcium and phosphate ions from specialized cellular compartments. The nucleation of mineral crystals at specific sites along the collagen fibers and the subsequent growth of these crystals to their mature dimensions over a period of days to weeks. The study of crystal defects, which are deviations from the perfect periodic arrangement of atoms in an ideal crystal lattice, is an essential component of understanding the real behavior of crystalline materials and the processes by which crystals form and grow. No real crystal is perfectly ordered. All contain some population of defects that arise during the growth process or that are introduced subsequently by thermal, mechanical, or chemical processes. Point defects, which involve the displacement or absence of individual atoms or ions, include vacancies, in which a lattice site that should be occupied is empty, interstitials, in which an extra atom occupies a position between the regular lattice sites, and substitutional defects, in which an atom of one type occupies a site that is normally occupied by an atom of a different type. The concentration of vacancies in a crystal at thermal equilibrium is described by the expression n/n equals exp ev/kt, where n is the number of vacancies, n is the total number of lattice sites, ev is the energy of vacancy formation, K is the Boltzmann constant with a value of 1.381 times 10 to the power of negative 23 joules per Kelvin, and T is the absolute temperature. For a typical metal such as copper, with a vacancy formation energy of approximately 1.0 electron volt, the equilibrium vacancy concentration at room temperature is on the order of 10 to the power of negative 17, which means that approximately 1 in every 100 quadrillion lattice sites is unoccupied. Line defects, or dislocations, are one-dimensional defects in which the regular arrangement of atoms is disturbed along a line that extends through the crystal. The two fundamental types of dislocations are edge dislocations, in which an extra half-plane of atoms is inserted into the crystal lattice, and screw dislocations, in which the lattice is displaced along the dislocation line in a manner that creates a helical ramp of atoms around the line. Dislocations play a critically important role in crystal growth. Because the presence of a screw dislocation on a crystal face provides a perpetual source of growth steps that enables the crystal to grow at much lower levels of supersaturation than would be required for the nucleation of new layers on a perfect, defect-free surface. This mechanism of crystal growth, known as the Burton-Cabrera-Frank (BCF) spiral growth mechanism, was proposed in 1951 by W. K. Burton, N. Cabrera, and F. C. Frank, and it provides a satisfying explanation for the experimental observation that crystals generally grow at supersaturation levels that are far too low to support the two-dimensional nucleation mechanism that would be required on a perfect crystal surface. Planar defects include stacking faults, in which the regular stacking sequence of atomic layers is disrupted, twin boundaries, in which two regions of a crystal are related by a mirror symmetry operation that is not part of the crystal's normal point group symmetry, and grain boundaries, which separate regions of different crystallographic orientation in a polycrystalline material. Twinning, in particular, is a common phenomenon in crystal formation that can arise through several different mechanisms. Growth twins form when an error in the stacking sequence occurs during crystal growth, producing two intergrown crystal domains that share a common lattice plane but have different orientations. Deformation twins form when mechanical stress causes a portion of the crystal to undergo a shear transformation that reorients the lattice. Transformation twins form when a high-temperature crystal phase transforms to a lower symmetry phase upon cooling, and the lower symmetry phase can adopt multiple orientations that are related by symmetry elements of the higher symmetry parent phase. The colors of crystals and minerals, which are among their most immediately appealing and noticeable properties, arise from a variety of physical and chemical mechanisms that are intimately related to the crystal structure and composition. Some minerals derive their color from the presence of specific chemical elements that are essential components of their crystal structure. Malachite, a copper carbonate hydroxide mineral with the formula Cu2CO3OH2, owes its distinctive green color to the presence of copper ions in the crystal structure, which absorb red and orange light through electronic transitions between different energy levels of the copper d orbitals. Similarly, the deep blue color of azurite, another copper carbonate hydroxide with the formula Cu3CO32OH2, arises from the same type of copper d orbital transitions, but the different coordination geometry of the copper ions in the azurite structure shifts the absorption bands to different wavelengths, producing blue rather than green. Other minerals owe their color to trace amounts of impurity elements that substitute for the normal constituents of the crystal structure. Pure corundum aluminum oxide is colorless, but the substitution of a small fraction of the aluminum ions by chromium ions, typically on the order of 1 to 2%, produces the deep red color of ruby, while the substitution of iron and titanium ions produces the blue color of sapphire. The green color of emerald, a variety of the mineral beryl, is caused by the substitution of small amounts of chromium and sometimes vanadium for aluminum in the beryl crystal structure. The purple color of amethyst, a variety of quartz, is caused by the presence of trace amounts of iron in the quartz lattice, combined with the effects of natural irradiation from surrounding radioactive minerals, which produces color centers that absorb green and yellow light. The phenomenon of fluorescence, in which a crystal absorbs light of one wavelength and re-emits it at a longer wavelength, is another optical property that is commonly observed in minerals and is related to the electronic structure of the constituent atoms and any impurities present. Fluorite, calcium fluoride, from which the term fluorescence derives its name, often fluoresces with a characteristic blue or violet glow under ultraviolet illumination, a phenomenon that is attributed to the presence of trace amounts of europium or other rare earth elements in the crystal structure. Willemite, a zinc silicate mineral, can exhibit a brilliant green fluorescence that is caused by the presence of manganese impurities, and the intensity of this fluorescence can be so strong that specimens of willemite from the Franklin mine in New Jersey have become prized collector's items and educational demonstration pieces. The practical applications of crystal formation processes extend far beyond the realm of academic mineralogy and encompass a vast range of industrial, technological, and medical fields. The growth of single crystals of silicon for use in semiconductor devices is one of the most economically significant crystal growing operations in the world, with the global market for silicon wafers amounting to billions of dollars annually. The Czochralski method, developed by the Polish chemist Jan Czochralski in 1916, is the most widely used technique for producing large single crystals of silicon. In this method, a seed crystal of silicon is dipped into a crucible of molten silicon, which has a melting point of 1,414 degrees Celsius, and then slowly withdrawn while being rotated. As the seed crystal is pulled upward, molten silicon crystallizes onto its lower end. extending the crystal and gradually building up a cylindrical ingot that can be up to 30 centimeters or more in diameter and over 1 meter in length. The crystals produced by the Czochralski method must have extraordinarily low defect densities and impurity concentrations, typically less than 1 part per billion for critical contaminants, in order to meet the stringent requirements of modern semiconductor manufacturing. The pharmaceutical industry relies heavily on the principles of crystal formation for the production of drug substances in specific crystalline forms that have the desired solubility, bioavailability, stability, and processing characteristics. Many pharmaceutical compounds are polymorphic, meaning that they can crystallize in multiple different crystal structures, and the selection and control of the appropriate polymorphic form is a critical aspect of drug development and manufacturing. The case of the anti-HIV drug ritonavir provides a cautionary tale about the importance of polymorph control. In 1998, approximately 2 years after the drug's initial approval and market launch, a previously unknown and more thermodynamically stable polymorph of ritonavir began to appear in manufacturing batches, and this new form had significantly lower solubility than the original form, rendering the oral capsule formulation of the drug ineffective. The appearance of this new polymorph necessitated the temporary withdrawal of the capsule formulation from the market and a costly reformulation effort, underscoring the practical importance of understanding and controlling crystal formation processes in the pharmaceutical context. The science of X-ray crystallography, which has been the single most important technique for determining the three-dimensional arrangement of atoms within crystals, has its origins in the work of Max von Laue, who in 1912 demonstrated that crystals could diffract X-rays, thereby proving simultaneously that X-rays are electromagnetic waves with wavelengths comparable to atomic spacing, and that crystals possess a regular periodic internal structure. The fundamental principle underlying X-ray diffraction is Bragg's law, formulated by William Henry Bragg and his son William Lawrence Bragg in 1913. Which states that constructive interference of X-rays reflected from parallel planes of atoms within a crystal occurs when the path difference between rays reflected from adjacent planes is equal to an integer multiple of the X-ray wavelength. Mathematically, Bragg's law is expressed as n lambda equals 2d sin theta, where n is an integer, lambda is the wavelength of the incident X-rays, d is the spacing between the diffracting planes, and theta is the angle of incidence measured from the plane surface. For copper K-alpha X-rays, which have a wavelength of 1.5406 angstroms, and are the most commonly used radiation source in laboratory X-ray diffractometers, the Bragg equation predicts diffraction peaks at specific angles that correspond to the various interplanar spacings present in the crystal structure. The younger Bragg, William Lawrence Bragg, used the diffraction data to determine the crystal structures of sodium chloride, potassium chloride, and diamond, becoming at the age of 25 the youngest person ever to receive the Nobel Prize in Physics, which he shared with his father in 1915. The sodium chloride structure determined by Bragg was notable for the then surprising finding that the crystal does not contain discrete sodium chloride molecules, but rather consists of an extended three-dimensional array of alternating sodium and chloride ions, each surrounded by 6 nearest neighbors of the opposite charge. This observation contributed to the development of the concept of ionic bonding and had a profound influence on the subsequent development of structural chemistry. In the century that has followed the Bragg's pioneering work, X-ray crystallography has been applied to determine the structures of hundreds of thousands of crystalline materials, ranging from simple inorganic salts to enormously complex biological macromolecules. The determination of the double helical structure of DNA by James Watson and Francis Crick in 1953, which was based in large part on X-ray diffraction photographs of DNA fibers taken by Rosalind Franklin and Maurice Wilkins, is perhaps the most famous example of the power of X-ray diffraction methods to reveal the structural basis of biological function. The first protein crystal structure, that of myoglobin, was determined by John Kendrew in 1958, and the subsequent decades have seen an explosion in the number of protein structures solved by X-ray crystallography, with the protein data bank now containing over 200,000 experimentally determined structures of biological macromolecules. The techniques used to grow crystals suitable for X-ray diffraction analysis vary considerably depending upon the nature of the material being crystallized. For small inorganic and organic molecules, common methods include slow evaporation of a saturated solution, slow cooling of a hot saturated solution, vapor diffusion, and the addition of an antisolvent to a solution of the compound. For protein crystals, which are particularly challenging to grow because of the large size, conformational flexibility, and chemical heterogeneity of protein molecules, specialized methods such as hanging drop vapor diffusion, sitting drop vapor diffusion, and microbatch under oil have been developed. In the hanging drop method, a small droplet of protein solution, typically 2 to 10 microliters in volume, is mixed with an equal volume of a precipitant solution and suspended from a glass cover slip above a reservoir containing the precipitant solution. As the drop equilibrates with the reservoir by vapor diffusion, the concentration of both protein and precipitant in the drop increases gradually, eventually reaching conditions that are favorable for the nucleation and growth of protein crystals. The process typically takes anywhere from a few hours to several weeks, and the conditions must be optimized through systematic screening of variables such as protein concentration, precipitant type and concentration, pH, temperature, and the presence of various additives. The use of synchrotron radiation sources for X-ray crystallography has greatly expanded the capabilities of the technique and has enabled the determination of structures from much smaller and more weakly diffracting crystals than would be possible with conventional laboratory X-ray sources. Synchrotron radiation is produced when charged particles, typically electrons, are accelerated to near the speed of light and forced to travel in curved paths by strong magnetic fields. The resulting electromagnetic radiation is extremely intense, highly collimated, and tunable over a wide range of wavelengths, making it an ideal source for X-ray diffraction experiments. Major synchrotron facilities dedicated to or including crystallography beamlines include the European Synchrotron Radiation Facility in Grenoble, France, the Advanced Photon Source at Argonne National Laboratory near Chicago, the Diamond Light Source in Oxfordshire, England, and the Spring 8 facility in Hyogo Prefecture, Japan, among many others worldwide. The determination of crystal structures by X-ray diffraction involves the collection of diffraction intensity data, which represent the magnitudes of the Fourier coefficients of the electron density distribution within the crystal, followed by computational analysis to reconstruct the three-dimensional electron density map from which the positions of individual atoms can be determined. The central challenge in this process is the so-called phase problem, which arises because the diffraction experiment provides information about the amplitudes but not the phases of the diffracted waves. And both pieces of information are needed to calculate the electron density by Fourier transformation. Various methods have been developed to solve the phase problem, including the Patterson method, which uses the squared amplitudes to construct a map of interatomic vectors, direct methods, which use mathematical relationships between the phases of different reflections to determine the phases directly from the measured amplitudes, and molecular replacement, which uses a known structure of a related molecule as a starting model to estimate the phases for the unknown structure. The growth of crystals from the vapor phase, in addition to the natural example of snowflake formation discussed earlier, encompasses a number of technologically important processes that are used to produce thin films, coatings, and bulk crystals of various materials. Physical vapor deposition methods, including thermal evaporation, sputtering, and molecular beam epitaxy, involve the transfer of material from a source to a substrate through the gas phase, with the deposited material crystallizing on the substrate surface under carefully controlled conditions. Molecular beam epitaxy, or MBE, is a particularly precise technique in which beams of atoms or molecules are directed at a heated substrate in an ultra-high vacuum environment, allowing the growth of epitaxial crystalline films with atomic-level control over composition and thickness. MBE has been instrumental in the development of semiconductor heterostructures, quantum wells, and supralattices that form the basis of many modern electronic and optoelectronic devices, including laser diodes, light-emitting diodes, and high electron mobility transistors. Chemical vapor deposition, or CVD, is another widely used technique for the growth of crystalline thin films and coatings, in which gaseous precursor compounds are introduced into a reaction chamber and undergo chemical reactions on or near the surface of a heated substrate, depositing a solid crystalline film. The CVD growth of diamond, which has been a topic of intense research and development activity since the 1980s, involves the decomposition of a carbon-containing gas, typically methane, in a hydrogen-rich atmosphere at substrate temperatures of approximately 700 to 1000 degrees Celsius. Under these conditions, carbon atoms are deposited onto the substrate and incorporate into the diamond crystal lattice rather than the graphite structure. Because the hydrogen atmosphere preferentially etches away graphitic carbon while leaving diamond carbon intact. CVD diamond films are used in a variety of applications, including cutting tools, heat sinks, optical windows, and, increasingly, in electronic devices that exploit the exceptional thermal conductivity, electrical insulation, and radiation hardness of diamond. The phenomenon of epitaxial crystal growth, in which a crystalline film grows on a crystalline substrate with a definite orientational relationship between the film and substrate lattices, is of central importance in semiconductor technology and in the fabrication of advanced electronic devices. Homoepitaxy refers to the growth of a film of the same material as the substrate, as in the growth of a silicon film on a silicon wafer, while heteroepitaxy refers to the growth of a film of a different material, as in the growth of gallium arsenide on a silicon substrate. The quality of an epitaxial film depends critically on the lattice mismatch between the film and substrate materials, which is defined as the relative difference in their lattice parameters. For gallium arsenide, with a lattice parameter of 5.6533 angstroms, grown on silicon, with a lattice parameter of 5.4310 angstroms, the lattice mismatch is approximately 4.1%, which is large enough to generate significant densities of threading dislocations and other defects in the growing film unless special measures are taken to accommodate the strain. The study of crystal symmetry has been greatly facilitated by the development of mathematical tools from the field of group theory, which provides a rigorous framework for describing and classifying the symmetry operations that leave a crystal structure unchanged. A symmetry operation is any geometric transformation, such as a rotation, reflection, inversion, or translation, that maps the crystal structure onto itself. The set of all symmetry operations that leave a crystal unchanged, together with the operation of composition, forms a mathematical group. And the classification of these groups is the basis for the systematic enumeration of all possible crystal structures. The 32 crystallographic point groups, which describe the rotational and reflective symmetry elements present at a single lattice point, can be derived from the requirement that rotational symmetry operations in a crystal must be compatible with the translational periodicity of the lattice, which restricts the allowed rotation angles to multiples of 60 degrees, 90 degrees, 120 degrees, 180 degrees, and 360 degrees, corresponding to 6-fold, 4-fold, 3-fold, 2-fold, and 1-fold rotational symmetries, respectively. 5-fold rotational symmetry, which would correspond to a rotation angle of 72 degrees, is not compatible with translational periodicity in a crystal and is therefore absent from the list of crystallographic point groups, a restriction that was considered absolute until the discovery of quasicrystals in 1984. The discovery of quasicrystals by the Israeli materials scientist Dan Shechtman on April 8, 1982, in a rapidly solidified alloy of aluminum and manganese, challenged the long-held assumption that all crystalline materials must possess translational periodicity. The electron diffraction pattern obtained from Shechtman's sample exhibited sharp Bragg diffraction spots arranged with icosahedral symmetry, including five-fold rotational axes that are forbidden in conventional crystallography. The publication of these results in 1984 was initially met with considerable skepticism and even hostility from some quarters of the scientific community, with the eminent chemist Linus Pauling famously declaring that there are no quasicrystals, only quasi-scientists. However, subsequent experimental and theoretical work confirmed the existence of quasicrystalline phases in a wide range of metallic alloy systems and the mathematical framework of aperiodic tilings, particularly the Penrose tiling developed by the British mathematician Roger Penrose in the 1970s. Provided a theoretical basis for understanding how a structure can possess long-range order and sharp diffraction spots without possessing translational periodicity. Shechtman was awarded the Nobel Prize in Chemistry in 2011 for his discovery, which fundamentally expanded the definition of what constitutes a crystal. The industrial crystallization of various chemical products, including pharmaceuticals, agrochemicals, food ingredients, and specialty chemicals, is a major area of chemical engineering that involves the design and operation of crystallizers to produce crystals with specified properties such as purity, particle size distribution, crystal habit, and polymorphic form. Batch crystallizers, in which a fixed volume of solution is processed through a cycle of supersaturation generation, nucleation, growth, and crystal harvesting, are commonly used for small-scale and specialty applications, while continuous crystallizers, in which feed solution is continuously added and product crystals are continuously removed, are preferred for large-scale commodity operations. The most common methods for generating supersaturation in industrial crystallizers include cooling, in which the temperature of a saturated solution is reduced to decrease the solubility of the solute, evaporation, in which solvent is removed by heating to increase the concentration of solute, anti-solvent addition, in which a miscible liquid in which the solute is insoluble is added to the solution, and reactive crystallization, in which two or more dissolved reactants combine to form a product that is less soluble than either of the reactants alone. The control of crystal size distribution in industrial crystallization is a matter of considerable practical importance, since the particle size affects downstream processing operations such as filtration, washing, drying, and milling, as well as the final product properties such as dissolution rate, bioavailability, flow characteristics, and appearance. The crystal size distribution in a batch crystallizer is determined by the interplay of nucleation and growth kinetics, and the challenge for the process engineer is to design operating conditions that produce the desired balance between these two competing processes. High levels of supersaturation favor rapid nucleation, producing many small crystals, while lower levels of supersaturation favor growth of existing crystals over the formation of new nuclei, tending to produce fewer but larger crystals. Seeding, in which a known quantity of small crystals is added to the crystallizer at a controlled point in the process, is a widely used technique for controlling the onset of nucleation and steering the crystal size distribution toward the desired target. The purification of chemical substances by crystallization, known as recrystallization, takes advantage of the fact that the crystal growth process is inherently selective, tending to incorporate only those molecules or ions that fit properly into the crystal lattice and excluding impurities that have different sizes, shapes, or charges. The effectiveness of recrystallization as a purification technique depends upon the relative solubilities of the desired substance and the impurities in the chosen solvent, and the best results are obtained when the desired substance has a solubility that varies strongly with temperature, while the impurities are either much more soluble or much less soluble than the desired substance under the crystallization conditions. In a typical recrystallization procedure, the impure substance is dissolved in a minimum amount of hot solvent. The solution is filtered to remove any insoluble impurities, and then the filtrate is allowed to cool slowly, producing crystals of the purified substance that are collected by filtration. The purity of the recrystallized product can be assessed by melting point determination, since the presence of impurities typically depresses and broadens the melting point of a crystalline substance relative to the sharp, well-defined melting point of the pure material. The formation of crystals in geological environments spans an enormous range of temperatures, pressures, and chemical conditions, and the study of these natural crystallization processes has been a central concern of the geological sciences since their inception as a formal discipline. Igneous crystallization, as noted previously, occurs at temperatures ranging from approximately 600 to over 1200 degrees Celsius for common silicate minerals, and the sequence of mineral crystallization from a cooling magma is determined by the thermodynamic stability fields of the various mineral phases as functions of temperature, pressure, and composition. The phase diagrams that describe these stability fields have been determined through decades of painstaking experimental work in high-temperature, high-pressure laboratories, and the resulting data constitute one of the most important foundations of modern petrology. The binary phase diagram for the system diopside anorthite, which was determined experimentally by Norman Bowen in 1915 and has served as a pedagogical cornerstone of igneous petrology ever since, illustrates many of the fundamental principles of crystallization from a silicate melt. Diopside, a pyroxene mineral with a composition CmGc2O6, has a melting point of 1,391 degrees Celsius, while anorthite, a plagioclase feldspar with a composition call 2C2O8, has a melting point of 1,553 degrees Celsius. A melt of intermediate composition, say 50 weight % diopside and 50 weight % anorthite, begins to crystallize upon cooling at a temperature determined by the liquidus curve, which for this composition is approximately 1,274 degrees Celsius. At this temperature, crystals of anorthite begin to form from the melt, and as crystallization proceeds and anorthite is progressively removed from the liquid, the composition of the remaining melt shifts toward the diopside-rich side of the diagram. The temperature of the melt decreases along the liquidous curve until the eutectic point is reached at approximately 1274 degrees Celsius and a composition of approximately 42% weight anorthite, at which point diopside begins to crystallize simultaneously with anorthite, and both minerals continue to crystallize at the constant eutectic temperature until all of the remaining liquid has solidified. Metamorphic crystallization occurs when pre-existing rocks are subjected to changes in temperature, pressure, or chemical environment that cause the original mineral assemblage to become thermodynamically unstable and to transform into a new assemblage that is stable under the new conditions. The temperatures and pressures at which metamorphism occurs range from approximately 200 degrees Celsius and 2 kilobars for low-grade metamorphism to over 800 degrees Celsius and 10 kilobars or more for high-grade metamorphism and ultra-high-pressure metamorphism. The mineral reactions that occur during metamorphism often involve the growth of new crystalline phases at the expense of pre-existing ones, and the textures and microstructures produced by these reactions provide valuable information about the conditions and mechanisms of metamorphism. Garnet, a group of silicate minerals with the general formula X3Y2CO4, 3 where X is a divalent cation such as iron, magnesium, calcium, or manganese, and Y is a trivalent cation such as aluminum, iron, or chromium, is one of the most commonly studied metamorphic minerals because of its resistance to subsequent alteration and its tendency to preserve compositional zoning that records the changing conditions during crystal growth. The growth of garnet crystals during regional metamorphism typically begins at temperatures of approximately 500 to 550 degrees Celsius in pelitic rocks, and the crystals may continue to grow over a temperature range of several hundred degrees as metamorphic conditions intensify. The compositional zoning within a garnet crystal, which can be revealed by electron microprobe analysis, typically shows a systematic variation from a manganese-rich and iron-poor core to a manganese-poor and iron-rich rim, reflecting the progressive depletion of manganese from the surrounding matrix as garnet growth proceeds and the changing temperature-dependent partitioning of iron and magnesium between garnet and the coexisting minerals. The formation of pegmatite crystals represents one of the most dramatic examples of crystal growth in geological environments. Pegmatites are extremely coarse-grained igneous rocks that form from the final, volatile-enriched residual liquids produced during the crystallization of granitic magmas. The high concentrations of water, boron, fluorine, lithium, and other volatile and fluxing components in pegmatitic melts dramatically reduce the viscosity of the melt and enhance the diffusivity of dissolved components, creating conditions that are exceptionally favorable for the growth of large crystals. Individual crystals and pegmatites can attain truly extraordinary dimensions. A crystal of spodumene, a lithium pyroxene, found in the Etta Mine in the Black Hills of South Dakota, measured approximately 12.8 meters in length and weighed an estimated 37 tons. Crystals of beryl exceeding 5 meters in length have been reported from pegmatites in Madagascar, and mica books over 4 meters in diameter have been found in pegmatites in India and Brazil. The formation of crystals in sedimentary environments occurs through a variety of mechanisms, including the direct precipitation of minerals from seawater or lake water, the replacement of pre-existing minerals by new phases, and the growth of authigenic minerals within the pore spaces of sediments during diagenesis. The formation of evaporite minerals, discussed earlier in the context of seawater evaporation, is one of the most volumetrically significant examples of crystal formation in sedimentary environments. The Permian Age Zechstein evaporite sequence of northwestern Europe, which was deposited approximately 250 to 260 million years ago in a large, restricted marine basin, contains individual beds of halite and potash salts that are tens of meters thick and extend over thousands of square kilometers, representing the crystallization of enormous quantities of dissolved salts from evaporating seawater over periods of millions of years. The formation of diagenetic concretions, which are roughly spherical or ellipsoidal masses of mineral cement that grow within sedimentary rocks, provides an interesting example of crystal formation in the subsurface environment. Concretions form when dissolved mineral matter, typically calcite, siderite, or pyrite, precipitates from pore waters and cements the surrounding sediment grains together. The growth of concretions is typically driven by local variations in the chemical conditions within the sediment, such as variations in pH, redox potential, or the concentration of dissolved ions. And the rate of concretion growth depends upon the rate of supply of dissolved mineral matter to the growing concretion surface by diffusion through the pore water. Typical growth rates for diagenetic concretions have been estimated at approximately 0.001 to 0.1 millimeters per year, meaning that a concretion 1 meter in diameter may have taken anywhere from 5,000 to 500,000 years to form. The role of microorganisms in crystal formation has become an increasingly recognized and actively studied aspect of geomicrobiology in recent years. Many species of bacteria and archaea are capable of inducing the precipitation of crystalline minerals, either as a direct consequence of their metabolic activities or through the creation of microenvironmental conditions that favor mineral nucleation and growth. Sulfate-reducing bacteria, for example, produce hydrogen sulfide as a byproduct of their anaerobic respiration. And this hydrogen sulfide can react with dissolved metal ions in the surrounding environment to precipitate crystalline metal sulfides, including pyrite, iron sulfide, which is the most abundant sulfide mineral in the Earth's crust. Iron oxidizing bacteria, conversely, can promote the precipitation of iron oxyhydroxide minerals by catalyzing the oxidation of dissolved ferrous iron to ferric iron, which is much less soluble and readily precipitates as crystalline or poorly crystalline ferrihydrite, goethite, or lepidocrosite. The formation of crystals under extreme conditions of temperature and pressure, such as those found deep within the Earth's interior, is a topic of considerable current research interest that has implications for understanding the structure, composition, and dynamics of the Earth's mantle and core. At depths greater than approximately 660 kilometers, corresponding to pressures above approximately 24 gigapascals, the common upper mantle minerals olivine and pyroxene are no longer stable and are replaced by denser crystal structures that can accommodate the higher pressures. The most abundant mineral in the lower mantle is believed to be bridgmanite, a magnesium-iron silicate with a perovskite crystal structure and the approximate composition Mg, FeCO3, which is stable at pressures between approximately 24 and 125 gigapascals and temperatures of several thousand degrees Celsius. Bridgmanite was named in 2014 in honor of the Nobel Prize-winning physicist Percy Williams Bridgman, who pioneered the study of materials under high pressure in the first half of the 20th century. At the very center of the Earth, where pressures reach approximately 360 gigapascals and temperatures are estimated to be between 5,000 and 7,000 degrees Celsius. The iron-nickel alloy that constitutes the inner core exists in a crystalline state. The crystal structure of iron under inner core conditions has been the subject of considerable debate among mineral physicists, with the hexagonal close-packed structure and the body-centered cubic structure both having been proposed as the stable phase. Recent theoretical calculations and experimental studies using diamond anvil cells and laser heating suggest that the hexagonal close-packed structure is the most likely stable phase of iron at the pressure and temperature conditions of the inner core. Although the presence of light elements such as silicon, sulfur, oxygen, and carbon, which are believed to be dissolved in the core alloy, may influence the relative stability of different crystal structures. The study of crystal formation in extraterrestrial environments has expanded dramatically in recent decades with the advent of increasingly sophisticated instruments for the remote and in situ analysis of planetary surfaces, and with a continued collection and analysis of meteorites and other extraterrestrial samples. Meteorites, which are fragments of asteroids, comets, and other solar system bodies that have survived passage through the Earth's atmosphere and landed on the surface, contain a rich variety of crystalline minerals that provide information about the conditions of crystal formation in the early solar system. Chondritic meteorites, the most common type, contain small, roughly spherical objects called chondrules, which are composed of silicate minerals such as olivine and pyroxene that crystallized from droplets of molten rock in the solar nebula approximately 4.567 billion years ago. The sizes of chondrules typically range from approximately 0.1 to 1 millimeter in diameter, and the textures of the crystals within them, including porphyritic, barred olivine, and radial pyroxene textures, provide clues about the cooling rates and thermal histories of the molten droplets from which they formed. The iron meteorites, which are composed primarily of iron-nickel alloy, contain large crystals that can be revealed by cutting, polishing, and etching the meteorite surface with a dilute acid solution. The resulting pattern of intersecting bands, known as the Widmanstätten pattern, is formed by the intergrowth of two iron-nickel phases, kamacite and taenite, that exsolved from a single homogeneous parent phase during the extremely slow cooling of the meteorite parent body over millions of years. The widths of the kamacite bands in the Widmanstätten pattern are directly related to the cooling rate of the meteorite, with wider bands indicating slower cooling and narrower bands indicating faster cooling. Typical cooling rates for iron meteorites range from approximately 1 to 100 degrees Celsius per million years, which corresponds to cooling within the metallic cores of asteroid-sized bodies with diameters of approximately 10 to 200 kilometers. The Martian meteorites, a small group of achondritic meteorites that are believed to have been ejected from the surface of Mars by large impact events, contain crystalline minerals that formed under conditions characteristic of the Martian crust and mantle. These meteorites, which include the shergottites, nakhlites, and chassignites, contain primary igneous minerals such as pyroxene, olivine, and plagioclase feldspar, as well as secondary minerals such as carbonates, sulfates, and iron oxides that formed through interaction with Martian fluids. The ALH 84001 meteorite, a Martian orthopyroxenite discovered in the Allan Hills region of Antarctica in 1984, attracted widespread scientific and public attention in 1996 when a team of NASA scientists reported the presence of possible microfossils and other features that they interpreted as evidence for past life on Mars. Although this interpretation remains highly controversial and is not accepted by the majority of the scientific community, the carbonate crystals in ALH 84001, which formed approximately 3.9 billion years ago, provide valuable information about the conditions of crystal formation in the early Martian environment, including the temperature, pH, and composition of the fluids from which they precipitated. The continuing advancement of analytical techniques and computational methods promises to further deepen our understanding of crystal formation processes in the years and decades to come. Developments in electron microscopy, including the advent of aberration-corrected scanning transmission electron microscopy, now allow the direct imaging of individual atoms within crystal structures with a spatial resolution better than 1 angstrom. Time-resolved X-ray diffraction experiments at synchrotron and free electron laser facilities can follow the structural evolution of crystals on timescales as short as femtoseconds, providing unprecedented insight into the dynamics of phase transformations and crystal growth at the atomic level. Computational methods based on density functional theory and molecular dynamics simulations can now predict the structures and properties of crystals from first principles with sufficient accuracy to guide the discovery and design of new crystalline materials with tailored properties for specific applications. The field of crystal engineering, which seeks to design and synthesize crystalline materials with predetermined structures and properties by controlling the intermolecular interactions that govern crystal packing, has emerged as an active and productive area of research at the interface of chemistry, materials science, and solid-state physics. Metal-organic frameworks, or MOFs, are a class of crystalline materials that have attracted enormous interest in recent years because of their extraordinary structural diversity, tunability, and porosity. MOFs are constructed from metal ions or clusters connected by organic linker molecules to form extended three-dimensional frameworks with pore sizes and geometries that can be systematically varied by changing the identity of the metal and linker components. The internal surface areas of MOFs can exceed 7,000 square meters per gram, making them among the most porous materials known, and their potential applications span a wide range of fields, including gas storage and separation, catalysis, drug delivery, and sensing. As the foregoing discussion has attempted to illustrate, the formation of crystals is a phenomenon of extraordinary breadth and depth that touches upon virtually every branch of the natural sciences and has practical implications that extend far beyond the boundaries of academic research. From the slow growth of stalactites in limestone caves to the rapid solidification of volcanic glass, from the exquisitely controlled biomineralization of mollusk shells to the industrial production of semiconductor-grade silicon, the principles of crystal formation provide a unifying framework for understanding the solid state of matter in all its remarkable diversity and complexity. The subject is, in the end, one that rewards patient and detailed study, and the accumulation of knowledge in this field over the past several centuries represents one of the quieter, but no less significant achievements of human scientific endeavor. The atoms continue their patient work of arranging themselves into ordered arrays, following the same laws of thermodynamics and kinetics that have governed their behavior since the formation of the first minerals in the cooling remnants of ancient stellar explosions and the crystals that result, whether visible to the naked eye or detectable only through the most sensitive analytical instruments, stand as enduring testimonials to the fundamental tendency of matter to seek its most energetically favorable state. The liquid crystal state, which occupies an intermediate position between the fully ordered crystalline solid and the completely disordered isotropic liquid, represents a fascinating aspect of the broader science of crystal formation and ordering phenomena in condensed matter. Liquid crystals are materials whose molecules possess some degree of orientational order, and in some cases partial positional order, while retaining the ability to flow like a liquid. The existence of this intermediate state of matter was first recognized in 1888 by the Austrian botanist Friedrich Reinitzer, who observed that cholesterol benzoate appeared to have two distinct melting points, first transforming from a solid into a turbid, birefringent liquid at 145.5 degrees Celsius, and then clarifying into an isotropic liquid at 178.5 degrees Celsius. The German physicist Otto Lehmann subsequently studied these materials in detail and coined the term liquid crystal to describe their dual solid-liquid character. The three principal types of liquid crystal phases are the nematic phase, in which the rod-shaped molecules are aligned with their long axes approximately parallel, but have no long-range positional order, the smectic phase, in which the molecules are arranged in layers with their long axes parallel, providing one-dimensional positional order in addition to orientational order, and the cholesteric or chiral nematic phase, in which the director, the average orientation of the molecular long axis, rotates helically through the material with a characteristic pitch that can range from a fraction of a micrometer to several micrometers. The technological applications of liquid crystals, particularly in display devices, have had a transformative impact on modern life that would have been difficult to predict from Reinitzer's initial observations of cholesterol benzoate in the late 19th century. Liquid crystal displays, or LCDs, operate by exploiting the ability of an applied electric field to reorient the molecules in a thin layer of liquid crystal material sandwiched between two transparent electrodes, thereby modulating the transmission of polarized light through the device. The twisted pneumatic LCD, which was invented independently by James Ferguson in the United States and by Martin Schatt and Wolfgang Helfrich in Switzerland in 1970 and 1971, respectively, was the first commercially successful liquid crystal display technology and remains the basis for many of the display screens that surround us in our daily lives, from digital watches and calculators to computer monitors and television screens. The global liquid crystal display market was valued at approximately $200 billion in the early 2020s and continues to be one of the largest and most important sectors of the electronics industry. Returning to more conventional crystalline materials, the phenomenon of crystal twinning deserves further elaboration, as it is one of the most commonly encountered features of natural and synthetic crystals and provides important information about the conditions under which the crystal formed. As mentioned briefly in an earlier section, twinning occurs when two or more crystal domains are related by a symmetry operation that is not part of the crystal's normal point group symmetry, resulting in an intergrown composite that displays an apparent symmetry higher than that of the individual crystal. Contact twins, in which the two individuals share a common composition plane, and penetration twins, in which the two individuals appear to interpenetrate each other, are the two most common morphological types. The Carlsbad twin of orthoclase feldspar, in which two monoclinic crystals are related by a 180-degree rotation about the C-axis, and the Japan twin of quartz, in which two trigonal crystals are related by a 180-degree rotation about a direction inclined at approximately 84 degrees to the C-axis, are among the most well-known and frequently illustrated examples of twinning in mineralogical textbooks. The phenomenon of crystal habit modification by impurities and additives has been studied extensively because of its importance in industrial crystallization, where the control of crystal shape is often as important as the control of crystal size and purity. The mechanism by which impurities modify crystal habit typically involves the selective adsorption of the impurity molecules onto specific crystal faces, where they block the approach and incorporation of additional growth units and thereby reduce the growth rate of those phases. Since the phases that grow most slowly become the largest and most prominent in the final crystal, the selective inhibition of growth on certain phases can dramatically change the overall shape of the crystal. For example, the addition of small amounts of urea to a crystallizing solution of sodium chloride changes the crystal habit from the normal cubic shape, in which the 6 cube faces are equally developed, to an octahedral shape, in which the 8 octahedral faces become dominant, because the urea molecules preferentially adsorb onto and inhibit the growth of the octahedral faces, while leaving the cube faces to grow rapidly and eventually disappear from the crystal surface. The crystallization of ice, which is by far the most abundant crystalline material on the surface of the Earth, presents a number of unique and interesting features that distinguish it from the crystallization of most other common substances. Ice, the ordinary form of ice that exists at atmospheric pressure and temperatures below 0 degrees Celsius, has a remarkably open crystal structure in which each water molecule is hydrogen bonded to 4 nearest neighbors in a tetrahedral arrangement, resulting in a relatively low density of 0.917 grams per cubic centimeter, which is approximately 8% lower than the density of liquid water at 0 degrees Celsius. This anomalous expansion upon freezing, which is a consequence of the open tetrahedral structure of ice, is responsible for the familiar phenomenon of ice floating on water and has profound implications for the behavior of freshwater lakes, rivers, and ocean surfaces in cold climates. The phase diagram of water ice reveals an astonishing diversity of high-pressure crystalline polymorphs, with at least 18 distinct ice phases having been identified and characterized to date. Ice 2, which is stable at pressures between approximately 200 and 400 megapascals at temperatures near -35 degrees Celsius, has a rhombohedral crystal structure with a density of 1.17 grams per cubic centimeter. Ice 3, stable at somewhat lower pressures around 300 megapascals and temperatures near -25 degrees Celsius, has a tetragonal structure with a density of 1.14 grams per cubic centimeter. Ice 7, which is stable at pressures above approximately 2 gigapascals, has a body-centered cubic arrangement of oxygen atoms with a density of 1.65 grams per cubic centimeter, nearly twice the density of ordinary ice. At the highest pressures accessible to laboratory experiments, above approximately 50 gigapascals, ice transforms into a superionic phase in which the oxygen atoms are locked in a crystalline lattice, while the hydrogen atoms diffuse freely through the structure like a liquid, a state of matter that is believed to exist in the interiors of the ice giant planets Uranus and Neptune. The formation of frost crystals on cold surfaces is a common example of crystal growth from the vapor phase that can be observed on any cold winter morning. Frost forms when water vapor in the air condenses directly as ice on surfaces whose temperatures are below the frost point, which is the temperature at which the air becomes saturated with respect to ice. The morphology of frost crystals depends upon the temperature of the surface and the humidity of the surrounding air, and under favorable conditions. Frost can form elaborate dendritic and fern-like patterns on glass windows that have long been admired for their beauty. The physics of frost pattern formation involves the interplay of diffusion-limited growth, in which the supply of water vapor to the growing crystal surface is controlled by diffusion through the air, and crystallographic anisotropy, which causes the crystal to grow preferentially along certain crystallographic directions. The resulting dendritic patterns are examples of fractal growth, in which the overall shape of the crystal is self-similar across a range of length scales, and the mathematical analysis of these patterns has connections to the broader theory of pattern formation in non-equilibrium systems. The role of crystal formation in the water cycle and in atmospheric processes extends well beyond the formation of snowflakes and frost. Ice crystals in the upper troposphere and stratosphere play an important role in the formation of cirrus clouds, which cover approximately 30% of the Earth's surface at any given time and have significant effects on the planet's radiation budget and climate. The nucleation of ice crystals in the atmosphere can occur by homogeneous freezing of supercooled water droplets at temperatures below approximately -38 degrees Celsius, or by heterogeneous nucleation on ice-nucleating particles such as mineral dust, biological particles, and soot at warmer temperatures. The microphysical properties of ice crystals in clouds, including their size, shape, and number concentration, influence the optical properties of the clouds and their interactions with incoming solar radiation and outgoing terrestrial radiation, making the accurate representation of ice crystal formation processes in climate models a topic of ongoing scientific importance. The solidification of metals and alloys, which is fundamentally a crystal formation process, is the basis of the entire metals industry and has been practiced by human civilizations for thousands of years. The casting of molten metal into molds to produce shaped objects was already well developed in the Bronze Age, approximately 3,000 to 5,000 years ago, and the basic principles of metal solidification, including the nucleation and growth of crystalline grains, the formation of dendrites, and the development of solidification microstructures, were established through scientific investigation in the 19th and 20th centuries. When a molten metal is poured into a mold and allowed to cool, crystallization begins at the mold walls, where the cooling rate is highest, and proceeds inward as the thermal gradient drives a solidification front toward the center of the casting. The first crystals to form at the mold wall are typically small and randomly oriented, forming a thin chill zone of fine equiaxed grains. Behind the chill zone, competitive growth among grains with different orientations leads to the development of elongated columnar grains that grow perpendicular to the mold wall in the direction of the thermal gradient. In the center of the casting, where the cooling rate is lowest and the melt is approximately isothermal, equiaxed grains may nucleate independently in the remaining liquid and grow in all directions, producing a central zone of relatively large, randomly oriented grains. The dendritic morphology of solidifying metal crystals, in which the crystal develops a tree-like branching structure with primary, secondary, and higher-order arms, is a consequence of the instability of a planar solidification interface in the presence of constitutional supercooling. Constitutional supercooling occurs when the actual temperature gradient in the liquid ahead of the solidification front is less than the liquidus temperature gradient, which depends upon the composition gradient in the liquid, resulting from the redistribution of solute during solidification. When a small protuberance forms on the solidification interface, it extends into a region of the liquid that is more supercooled than the surrounding interface and therefore grows faster, amplifying the perturbation and leading to the development of dendritic arms. The spacing between the primary and secondary arms of the dendrites is determined by the cooling rate and the alloy composition, with faster cooling producing finer dendritic structures and correspondingly finer microstructures in the solidified material. The mechanical properties of cast metals, including their strength, ductility, and fracture resistance, are strongly influenced by the grain size and microstructure produced during solidification, and the control of solidification conditions to achieve desired microstructures is a central concern of metallurgical engineering. The formation of single crystals of metals and semiconductors by directional solidification techniques, in which a carefully controlled thermal gradient is used to produce a single continuous crystal from a melt, is essential for many advanced technological applications. The Bridgman method, named after Percy Bridgman, involves the slow withdrawal of a crucible containing the molten material from a furnace, causing the material to crystallize progressively from one end to the other. If a single crystal seed is placed at the cool end of the crucible, the entire charge can be solidified as a single crystal with the same crystallographic orientation as the seed. The Bridgman method is used to produce single crystals of a variety of materials, including the nickel-based superalloys used for turbine blades in jet engines, which must withstand temperatures in excess of 1,000 degrees Celsius and centrifugal stresses of several hundred megapascals during operation. The use of single crystal turbine blades, which eliminate grain boundaries that serve as sites for the initiation of creep and fatigue damage, represents one of the most demanding and commercially important applications of crystal growth technology in modern engineering. The science of crystal formation continues to evolve and expand, driven by the development of new experimental techniques, new computational methods, and new applications that demand crystalline materials with ever more precisely controlled properties. The growth of crystals in microgravity environments aboard the International Space Station, the use of machine learning algorithms to predict crystal structures and optimize crystallization conditions, and the development of new classes of crystalline materials such as covalent organic frameworks, perovskite solar cell materials, and topological insulators are among the many active frontiers of crystal science research. As our understanding of the fundamental processes governing crystal nucleation and growth continues to deepen, and as our ability to control these processes at the atomic and molecular level continues to improve, the formation of crystals will undoubtedly remain a subject of enduring scientific interest and practical importance for many years to come. The quiet, methodical assembly of atoms into ordered arrays, governed by the unchanging laws of physics and chemistry, proceeds with the same patient inevitability that has characterized it since the earliest moments of our planet's geological history, and the study of this process, with all its complexity and subtlety, offers a fitting subject for contemplation as the mind gradually releases its grip on the waking world and drifts toward the peaceful oblivion of sleep.